So good evening everyone. Welcome to the final problem solving session related to the structural analysis course. So this is your final week, that is week number 12 related to the structural analysis course, wherein we will try to solve the problems related to the topic what you have covered in this current week. So let me share my screen first, then we will discuss about that. I hope the screen will be visible to everyone. So let's start this session. So this is your week number 12, or you can say your final session related to structure analysis course. We used to solve all the problems related to the topics that you have covered in every week. So we started with a basic concept and we have reached up to a certain level where we can analyze a basic frame, a basic truss, as well as a basic beam. So whether that beam truss or you can say beam truss or frame is statically determinate or indeterminate, we have different methods to solve them to get to know what are the shear force and bending moment that are generated at different points of the section. So the course is designed to make you aware how the analysis of the stress of any structure, whether it is truss, bridge, or you can say truss, frame or beam, what kind of member is there. So when you are expected to calculate, or you can say when you are expected to analyze that structure, whether you are sufficient enough, or you can say whether you are capable of enough to determine the various forces that are acting at different joints, or you can say at different sections. So that is the main purpose for this course. So let me remind you about what you have covered in the last 11 weeks. So we started with analysis of beams for shear force and bending moments. Then, after determining how the shear force and bending moment is varying along different sections, that means when you have concentrated load, you have seen that the shear force is varying as a constant throughout the length of the beam. But when it comes to the uniformly distributed load, it is acting as a linear curve throughout the length. This variation changes to 2-degree curve when you have uniformly varying loading. Then we have seen how we will determine the static indeterminacy. So when your static indeterminacy, that is ds, is coming out to be 0, we call the structure to be statically determinate. And when it is not equal to 0, we call the structure of that particular degree. Okay. Then for different statically determinate structure, we have seen for trusses, we have seen method of joints and method of section. For trusses, or so sorry, for beams and frames, we have seen moment area method, conjugate beam method, and virtual load word method, and further direct integration method, unit load method. These all methods we have seen. After that, we have seen the effect of influence line diagram when you have moving load over a certain length of the beam. Then how you will use the influence line diagram and determine the reaction force as well as the maximum bending moment at that particular at any point of the section where you can determine the maximum as well as the maximum bending moment as well as the maximum shear force. Then we have went to analysis of indeterminate structures, where we have seen started with again with the trusses. We have seen how we can utilize method of consistent deformation. This method of consistent deformation is also applicable to beams as well as frame. Further, we have seen the displacement method, or you can say the stiffness method, in which we have seen different problems that can be solved using moment distribution method as well as slope deflection method. So today in this session, what we will do, we will make you we will introduce you to a certain kind of analysis that we call it as the direct stiffness method, wherein when the complexity of problem is too increased that you can't solve a part of the structure isolatedly. That means multiple structures are altering, and both of them have a coupled effect on each other. That means second is affecting the shear force as well as the bending moment diagram of the first one, and the first is also affecting the shear force and the bending moment diagram of the second one. So this is called the coupling effect. Currently, what problems we have faced? We have faced all the decoupled problems. That means there is no effect of the one span over the other span. But when there is an effect of the one span over the other span, so we will introduce you. This is not a course. This is not the topic which you need to be covered in detail for this particular level of course. When you will study the advanced level of the structural analysis, that is structural analysis 2, then you will be able to understand the total mechanism how this direct stiffness method works. So, giving you a brief overview, you started with the introduction of the direct stiffness method in this week. So, certain concepts are discussed in the different slides, or you can say different lectures that are provided to you on the NPTEL portal. So, what is stiffness method and what are the properties of a stiffness method? So, defining the properties of a stiffness method is a square and the symmetric matrix that we use in structural analysis purpose, and it relates beams with forces and displacement in which the diagonal element are always positive, as well as the sum of elements in any column is being zero. That means this is the property of the stiffness matrix, that in this the diagonal element can never be negative, as well as the sum of elements in any column will become equal to 0. So when they are not equal to 0, that means you have done some calculation error in calculating that, and then you can rectify that and then see whether the sum of all the values is coming out 0 or not. Another 7 properties that are mentioned here is the symmetry. That means it is a square and the symmetric matrix. What do you mean by symmetric matrix? That if you have a matrix A, its transpose will also be equal to A. Okay. Then we have positive diagonal elements. That means the diagonal elements will not have any negative number. Third property is the sum of elements in any column of the stiffness matrix is always 0. Okay, that we have seen in the starting line of this problem also. Further, the size of the matrix that corresponds to the number of degree of freedom is also defined. That means the number of degree of freedom that is there in the structure, that will define the size of the stiffness matrix. That means if you have 3 degree of freedom, then that means your stiffness matrix will be of 3 by 3 order. Further, flexibility, as we already know that stiffness is inverse of the flexibility. So on the same lines, stiffness matrix will also be the inverse of the flexibility matrix. Next point tells you that the stiffness matrix can be developed only when the structure is stable. So we have seen various equation that how we determine the stability of a structure. Okay, so whenever the structure is stable, then only we can determine the stiffness matrix of that particular structure. Further, these matrices are singular. That means their determinant are 0 and their matrix cannot be inverted. Okay, so these are the some of the properties related to stiffness matrix. You can keep some of them in mind while solving any problem related to matrices of the stiffnesses. So let's solve few problems related to this. So these are just a basic problems to let you know how the stiffness matrix works. So in this question, it is telling you, simple question, that you have to find the dimension of the global stiffness matrix to solve the following truss. So as we have already seen in the properties of the stiffness matrix, that the dimension of the stiffness matrix depends upon the number of degrees of freedom. Okay, so that means in indirect sense, this question is not asking you the size of the global stiffness matrix that might be not familiar to you. So in another sense, you can see that what is the degree of freedom of this structure. If you are calculating the degree of freedom of this structure, that means you are calculating the size of the stiffness matrix for this particular structure that is given to you. So let's start with calculating the degree of stiffness in this structure. So in this, at A, your dk A is 2. Okay, I think by this time you know how to determine the degree of or we can say degree of freedom of a structure. Similarly, in this case, you can see that at B also your dk is 2, and on the same lines at C your dkc is equal to 2. Therefore, your total dk will become 2 plus 2 plus 2 equal to 6. Therefore, or I will write this implies size of stiffness matrix is 6 by 6. Okay. So if I talk about how the degree of freedom will be there in the structure, so let me mark in the diagram. So I am marking the in the diagram. So these are the two degree of freedoms. Here also these are the two degree of freedoms. So here also these two are the degree of freedoms. Okay. So 1, 2, 3, 4, 5, 6 will give you 6 degree of freedom in this structure, and that will tell you the size of matrix to be equal to 6 by 6. Okay, fine. So let's move to next question. So in this case, your problems will not be very tough. It is only to provide you a glimpse of how the stiffness matrix looks like. Okay, so let's move to next question. So your next question is again, you have to determine the global stiffness matrix to solve the beam under any load condition. Okay, so in this question, loading is not given to you. You have to determine what will be the size of the global stiffness matrix. So as we already know that degree of freedom doesn't depend upon any loading condition. So we can find the degree of freedom for this structure, and then we can say that what will be the size of the stiffness matrix. So in this case, if you neglect the so in this case, you can see that degree of freedom in this structure will be at A, it will be like this. Same direction will be there at B. Same at C. And similarly, same at this will work at D also. Okay. So if we calculate total degree of freedom in this structure, it will accumulate to 1, 2, 3, 4, 5, 6, 7, 8. So as we have already mentioned, so I will write here according to property of stiffness matrix, the size of the stiffness matrix is dependent upon, not independent, it is dependent upon the degree of freedom. Let me write with the red pen. Degree of the freedom of the structure. So if I calculate dk in this case, so dk will come out as 2 plus 2 plus 2 and 2, that means equal to 8. Therefore, size of stiffness matrix will be 8 by 8. Okay, fine. Let's move to next question. So your next question is, when a vertical displacement without any rotation is applied at support B of a prismatic beam with both ends fixed of length L and flexural rigidity I, what is the moment induced at the support B? Okay, so the question is telling you have to provide a unit vertical displacement at the support B without providing any rotation. So let me first draw the beam. So how it will look like? So let's see, if you are having a fixed beam like this. So the question is telling you, if this beam bends like this, okay, like this, now it has undergone a displacement. So the question is telling you to take the displacement equal to 1. That means delta in this case, it is telling you to be equal to 1 unit. Okay, but due to this displacement, rotation as well as shear will occur in the beam. So let's see. So if we apply the rotation in the beam like this, okay, so this value will be equal to 6 EI upon L square. Okay, so you have to provide anti-clockwise moment at the free end to make the structure in equilibrium. Okay, due to this, since you are providing anti-clockwise moment to the structure, so to make the structure in equilibrium, a clockwise couple will act in the direction like this. So the couple will act in the clockwise direction. It will be having the value equal to 12 EI delta upon L cube. Okay. So this is all the forces as well as moment that will occur in the beam when you suffer a unit settlement at the support B. Okay. So what the question is now asking you? So the question is asking you what is the moment that will be induced at the support B. So moment induced at support B due to unit vertical displacement at B without rotation is 6EI delta upon L cube L square. You can ignore delta also because delta in this case is equal to 1. Okay. So this is how you will solve the problem when there is settlement in the structure. Now let's see what other questions are telling you. So in the next question, it is telling you that a unit rotation without any vertical displacement is applied at the support A of the prismatic beam AB with both the end fits of length L and flexural rigidity I. Now what will be the moment induced at the support A? Okay. So now the question is changed. Instead of providing a unit displacement at B, now you are providing unit rotation at A. So let's start this question with the fits beam. Okay. So this is your original condition when the both ends of the beam is fixed. Now the question is telling you that you are providing a unit rotation at the end A. So that means you have to provide unit rotation at the end A, but end A is a hinged end. End A is fixed end. So that means no rotation will be there. So now what we will do? We will change this structure into a prop cantilever with end A to have the hinge support. Okay, then only we can provide unit rotation. So this is your support A. Now if you provide unit rotation, how it will, how the reflected profile of the beam will look like. So let's say this is your unit rotation and it will have zero rotation at the end B. Okay, so let me mark a tangent in this direction. Okay, so this will give you a unit rotation in the clockwise direction equal to theta is equal to 1. Okay, so now when you provide unit rotation, you already know when your far end is fixed. So if you provide unit rotation, so the amount of moment generated will be equal to the flexibility coefficient that we have already defined in previous class, and its value is 4EI upon L. Okay, so when there is 4EI upon L in clockwise direction, so that means its carryover moment equal to 2EI upon L will also act in the fixed end point, that is at support B. That means it will be equal to 2EI upon L. Now this is the clockwise moment that is acting in the beam. So to provide the equilibrium to this structure, an anti-clockwise tuple needed to be provided. So this is the anti-clockwise tuple, and they will be having the values equal to 6ei upon L square, and here also it would be 6ei upon L square. Okay, so the moment that is induced at support A, so let me write at the bottom. So moment induced at support A due to unit rotation applied at support A will be equal to, you can write it here to be equal to 4ei upon L. Okay. Now let's see what the next other question is asking you. So the next question is asking you, when you are providing a unit rotation without any vertical displacement in a prismatic beam AB with both the end fits and of length L and flexural rigidity EI, what will be the moment induced at the support B? So continuing the same diagram, let me copy this diagram in the next page. Okay, as we have already defined all the values in this, so you can say that the moment induced at the support B will be equal to the carryover moment due to the unit rotation provided at the support A. So moment induced at B due to unit rotation applied at support A, that will be equal to two EI upon L. Okay, so this is how you will solve the problems related to this. Okay, so let's solve one more problem. So your next problem is, it is telling you that assume that you are calculating deflection at the free end of the cantilever beam subjected to some transverse loading conditions. Okay, so that means it is telling you you have a cantilever beam like this, and it is subjected to transverse loading condition. So any loading could be occur in this beam. Okay, now if the stiffness matrix of this linear beam is halved without changing any loading condition, then what will be the change in the deflection value at the free end now? Okay, that means it is telling you, if you have, like you can say, when you have a rigid material which is having a stiffness equal to K, now you are using a low stiffness material, or you can say less stiffness material, which is having the stiffness equal to K by 2. Okay, then what will be the deflection that will be observed? As you already know, as stiffness reduces, the deflection increases. Okay, so we will use this relation. Okay, so let me write. So we know P is equal to K times delta, where K is the stiffness of the beam. Now, when K dash will be equal to K by 2, okay, then it is telling you that loading will remain same. That means P is equal to K delta should remain equal to K dash delta dash. Okay, now if you substitute the value of K dash, that means K into delta will be equal to K by 2 into delta dash. Okay, this will give you the value of delta dash to be equal to twice of delta. Okay, so that means you will observe the deflection to be twice when your stiffness is reduced to half. Okay, so simple question, no big concepts that are involved in solving this problem. So let's solve one more problem. In this, it is telling you that stiffness of a that the stiffness matrix of a truss element is this. Now it is expecting you to calculate the flexibility matrix. So as per the property of the stiffness matrix, your flexibility matrix will become equal to inverse of your stiffness matrix. Okay, that means in this question, what is required for you to calculate the inverse of the stiffness matrix that is provided to you in solving the problem. So your K that is provided to you in this question is equal to EA into 2342. Okay. Now what is the formula to calculate stiffness? Oh, sorry, inverse. So first we will calculate determinant of this K matrix. So your determinant of K will become equal to 2 into 2 minus 4 into 3. That means it will be equal to 4 minus 12 equal to minus 8 into EA. Okay, EA I have missed, so I am writing it here, EA. Okay, now if we try to find cofactor matrix, so I will write COF of K, that will be equal to 2 will remain 2. Okay, your 3 will become minus 4 and your 4 will become minus 3 and this will remain 2. Now you are expected to calculate adjoint of this K matrix. So adjoint of K is equal to cofactor of K transpose. Okay, so that will be equal to 2 minus 3 minus 4 and again 2. Okay, now your flexibility matrix, let me write it here, that your flexibility matrix is equal to K inverse, and your K inverse is equal to 1 upon determinant of K multiplied by adjoint of K, and that will give you equal to 1 upon minus 8A EA into 2 minus 3 minus 4 2. Okay, so let's solve it further. So if we take 1 upon 4A outside, 1 upon 4 EA, that will give you the value as 1 minus 1 minus 1 point, I'm sorry, plus 1.5 minus 2, no, sorry, plus 2, and here minus 1. Okay, so this will become your flexibility matrix. Okay, so please remember this whenever it is expected to calculate flexibility matrix or stiffness matrix. What you have to do, you have to take inverse of stiffness matrix and flexibility matrix correspondingly. Okay, let's solve one more problem. So in this, it is given to you, find the stiffness matrix of the following beam with the flexural rigidity EI. Note the degrees of freedom are mentioned in the structure as given in the circle. So as with A end is fixed, so there will be no degree of freedom in the structure, whereas your end B is free. So in this, if we neglect the axial deformation, so you are having two degrees of freedom, that is 1 and 2, that is provided to you in the figure. Now what is expected to you? To calculate the stiffness matrix for this problem. So what we will do, we will first, we will use the superposition principle and isolate one separately and two separately, and then we will see effect of them, and then we will combine and we'll get to know the stiffness matrix correspondingly. So when only one is applying on the structure like this, so if you apply only one, okay, so when you apply one, that means you are providing a unit displacement in the structure like this. In the initial part, you have slope equal to 0, but finally you will be having the slope equal to 0. Okay, so that means this much displacement, and this displacement we represent as delta, and this delta we also can write to be equal to 1. Okay, so as we have already seen, when this case occurs, the anti-clockwise moment will have the value equal to 6 EI upon L square, and correspondingly anticlockwise moment will be generated at the fifth support equal to 6 EI delta upon L square. Since both are providing anticlockwise moment, so to make the structure in equilibrium, a clockwise moment of shear will be provided. So that will come out as like this. This will have the value equal to 12 EI delta upon L cube, and here it is 12 EI delta upon L cube. Okay, so these are the values that you have obtained when you have provided a unit displacement at the end B. Okay, so this will contribute to K11 equal to 12 EI delta divided by L cube, and K12 to be equal to minus 6 EI delta upon L square. Minus have come because of the convention that is provided to you in the question as clockwise to be positive and anti-clockwise to be negative. So similarly, when you provide a unit rotation at end B, so how the structure will behave? Let's see that. So when you provide unit rotation at end B, okay, so that means you have to convert this fixed support into hinge support, and you are providing a rotation, unit rotation at the free end. So if you mark this, so if you mark the tangent, okay, so your this theta will be equal to 1, and if this theta is coming, that means 4 EI upon L will come into picture because of free end, and its carryover moment will be equal to 2 EI upon L. Now since they are providing clockwise moment, so anti-clockwise shear couple will act. So anti-clockwise shear couple will be like this. It is having the value equal to 6 EI upon L square. Okay, same on the other side, 6 EI upon L square. Now this is your NA, this is your NB. Now your K21 will become equal to minus 6 EI upon L square, and your K22 will become equal to 4 EI upon L. Okay, so if we combine all the elements, so your K matrix will be, so K is defined as, in terms of 2 by 2 matrix, it is K11, K12, K21, K22, okay, and that will be equal to Substitute all the values that we have generated, that is 12 EI upon L cube minus 6 EI upon L square, again minus 6 EI upon L square, and finally 4 EI upon L. Now if you substitute all these values of L, so let's substitute the value of L. That will give you one common value, that is EI, and your rest all values will become 0.44 minus of 0.67, again minus of 0.67, and here 1.33. From this also you can confirm that your stiffness matrix here that is provided to you is square and symmetric. That is, when you do the transpose of this matrix, you will get the same value. Okay. So these are the some basic problems that you are expected to solve and then determine how the structure will behave under different complex conditions. Okay. So we will wrap up this session here. So this 12th week is only provided to you to provide you a glimpse of how the structural analysis in advanced stages will behave, and you should be able to look forward the problems in a broader way. So the introduction to direct stiffness method we have covered in this current week, and this will end your structural analysis course for this semester, which occurred from January till April. Okay, so what you have covered in this current week, let me summarize you in detail. So we started with the some basic thing, that what is structure. So we defined a structure that is a combination of different members bearing the loads at different points of the section. So to design these members, we need to know what are the reaction as well as the forces at different points of the section. Then only we can design the members. So to know the amount of forces acting on particular section, we need to do the analysis. So this is the basic course of civil engineering, where we will do the analysis of the loads at different points of the section. So we started with analysis of statically determinate structure. So how you define the statically determinate structure? When your number of unknowns in the equation are equal to the number of available equations. So how you define the number of available equations? Generally, we define it to be equal to number of equilibrium equations. But when you have some additional compatibility equation that is also available at the point of the at the middle of the beam or at any point of the beam, like you can say provision of internal hinge, so that provide you some additional compatibility equation to solve the beam. So that will also act as an available equation. So in that case, when you have one internal hinge, your number of available equations will become equal to 4. So after that, we have seen how to analyze the statically determinate structure using method of joints and method of sections. Then we have seen for beams and frames to various methods to solve them. We have seen moment distribution method, conjugate beam method, unit integration method, direct integration method, maculae method, method of virtual work. So all these methods we have covered for the statically determinate structures. After that, we have moved to loading, or you can say influence line diagram, where we have seen how the proportionality of load should be provided to obtain maximum bending moment and maximum shear at the different points of the span. So we have used Mueller-Bridge law principle in that. So after that, we introduced to you the force and the stiffness matrix method. So we have told you in the force method, your unknowns are your forces, reaction forces, whereas in case of displacement method, You have unknowns as your displacement at different points of the beam or any structure member. Then we have seen different force method and different structure stiffness method. So first we have solved for the force method using method of consistent deformations for both trusses as well as beams and frames. Then we have seen how to utilize the displacement method. In that we have seen how the slope deflection method can be utilized, how moment distribution method can be utilized to get the absolute bending moment and absolute shear force at the different points of the span. So finally, in today's week, we have seen how the stiffnesses matrix can be developed and how these stiffness matrix properties could influence and help in getting to know what will be the flexibility matrix, which is the inverse of the stiffness matrix to get from the available stiffness matrix. So I think this will cover all your doubts, whatever you have in this structure analysis course. You might have liked this course, and I think you should solve each and every problem in a better way so that your concept will get stronger day by day whenever you encounter any problem and you got stuck at that particular point, and when you try to look at that point that why you got stuck, so then you came to know that in this how the new concepts can be applied and you will be able to solve the problem in a easier way. So I will wrap up this session for today. I hope you have liked all the session. In case you want to provide any feedback, the feedback form is regularly circulated by NPTEL team. You can provide your feedback in that. So this will wrap up your structure analysis course. We will, if you have any doubts, you can ask them on Swayam portal. So let's in. I will help. One more session I think will be conducted. That will be a summary session in next few days. So till then, enjoy your weekend. Have a nice day, and do solve your problems as well as the assignments. So thank you everyone.